Gravitational waves are often described as ripples in the fabric of spacetime, caused by the acceleration of massive objects. A passing gravitational wave can be visualized as a wave that distorts spacetime, causing motionless test particles in its path to oscillate in a cruciform manner. This means that their mutual distance changes, but only by a tiny amount. More details will be provided later. It is often emphasized that gravitational waves are a key prediction of Albert Einstein's general theory of relativity from 1915. However, what is not frequently mentioned is that their existence was a topic of intense debate among scholars of relativity, including Einstein himself, especially in the early years. For example, in 1922, Arthur Eddington demonstrated that two types of waves proposed by Einstein were actually artifacts of the coordinate system he used, and could be manipulated to travel at any speed by choosing appropriate coordinates. This led Eddington to joke that these waves propagate at the speed of thought. However, in the following years, the physics community convinced itself that gravitational waves were a genuine phenomenon deserving experimental verification. First laboratory detection attempts date back to the 70s, when Joseph Weber started designing and building the first gravitational wave detectors, now known as Weber bars. In 1969, Weber claimed to have detected the first gravitational waves, and by 1970, he was detecting signals regularly from the galactic center. However, it soon turned out that Weber's results were spurious and non-reproducible by independent research groups with the same technique. In the 1970s, scientists accepted an indirect proof of the existence of gravitational waves. Russell A. Hulse and Joseph H. Taylor Jr. discovered the first binary pulsar in 1974. Over the next decade, observations of this pulsar showed a gradual decay of its orbital period, matching the loss of energy and angular momentum in gravitational radiation as predicted by general relativity. During the same period, it was realized that the laser interferometry technique could be sensitive enough to detect the tiny displacements caused by gravitational waves among stationary objects. Then, in the first decade of 2000, scientists managed to complete and run 3 4-kilometer arm laser interferometers, 2 in the US, the LIGO Observatory, and 1 in Italy, the Virgo Observatory. Finally, on September 14, 2015, the LIGO-Virgo collaborations made what they called the first direct observation of gravitational waves. They were detected only by the 2 LIGO interferometers, since the Virgo one was offline and undergoing an upgrade at that time. Scientists claim to have detected the gravitational waves generated by the merger of 2 black holes of about 36 and 29 solar masses at a distance of more than a billion light-years. They assert that the gravitational waves emitted by the cataclysmic merger of 2 black holes reached Earth as ripples in spacetime, subtly altering the 4-kilometer-long LIGO arms by just 1,000th of a proton's width. Moreover, the waveform detected by both LIGO observatories precisely matched the predictions of general relativity. Following this groundbreaking discovery, the collaboration achieved several subsequent detections. Now, I believe we need to take a step back and consider some common-sense points that seem to have been overlooked or avoided. Looking past all the hype, it appears to me that this situation is quite nonsensical from a physical standpoint. Let's break it down. Direct observation. The LIGO-Virgo collaboration claims to have made the first direct observation of gravitational waves, but in reality, there is nothing direct about it. The experimental design and data interpretation heavily rely on the assumed validity of general relativity, to the extent that the experimental results cannot be considered an independent verification of the theory or a direct observation of the phenomenon. It's important to be cautious, because internal consistency doesn't always equate to physical truth. It can sometimes lead to self-deception. Additionally, the data acquisition and elaboration involved extensive and complex statistical manipulation and noise reduction, which are also theory-dependent. Therefore, labeling the entire process as a direct observation may not be an accurate representation of the evidence. Sensitivity. No one seems to have turned up their nose when the collaboration claimed that LIGO has been able to detect a change in distance between the interferometer's mirrors that is down to 1/10,000th the width of a proton. Pause and repeat, 1/10,000th the width of a proton. Moreover, that displacement was due to something generated more than a billion light-years away. Honestly speaking, How could a sane person really believe that this makes even the slightest sense? Repeatability. Every experimental result that cannot be repeated by truly independent groups is not science and should not be trusted, no matter how much money has been invested in it, period. I'm specifically referring to the detection of gravitational waves in general, not to a specific and unique event. That's science, baby. We have to accept this, and we need to restore discipline and credibility in the practice of science. In fact, what Weber did was science. Other truly independent groups tried to replicate his results and failed. The fact that nowadays we are forced to rule out a similar possibility with LIGO Virgo does not mean that they are right. What would have happened if Weber's apparatus were too big, complex, and expensive, like the LIGO Virgo ones, to be duplicated by other truly independent research groups, and his measurements were only more plausible from a theoretical point of view? Well, we would be here celebrating Weber's Nobel Prize.